Okay, so in this lab here, we're going to be creating a stock solution of cobalt-2 nitrate. We're going to perform some dilutions to that there. We're going to be running through these dilutions through a spectrometer to create what's called a calibration plot. And using that linear relationship, we're going to try to interpolate the concentration of some unknown. So this is the first part. We're going to create our solution. So I have our cobalt-2 nitrate here. We're going to be making our solution here in a beaker. Make sure your electronic balance here starts off at 0 here. I'm going to just put the empty beaker on top of it. I can tear the scale here, so make sure it's 0 to begin with. Okay. Sometimes if the balance isn't level here, sometimes it has trouble actually getting to 0. All right, but there we go. We have a 0. My lab handout, it tells me to weigh out 4.66 grams. Of course, we want to get as close to 4.66 as we can. If we go a little bit over, it's not the end of the world. You would just record that mass down with any associated error, and then you just use that for your calculation. Always better to just start off with less. If you need more, you can always go back for more of this chemical. If you happen to take too much here, it's best practice not to put the chemical back into the stock container, just in case it contaminates the rest of the stock bottle. So, again, for this experiment here, we're starting off aiming for 4.66, okay? So I'm really close here. I'm just gonna add maybe just a quick small little tap here, okay? Again, any extra I don't want to be putting back in the bottle. I know I've gone over, that's okay. I'm going to record that mass down anyways. Just going to toss that away here. I have 4.79 grams. Let's do a plus or minus 0.01. Again, what we want to do is we want to make a solution of this inside a volumetric flask. We have a 100 milliliter volumetric flask there. Unfortunately, because of the narrow neck, it's really hard to dissolve powder in there. So what I'm going to do here is, as I add water, I'm just going to add water to the beaker first. Just make sure it is under 100. We're going to eventually put it in the volumetric here, transfer some rinsings back into the volumetric, and then making it up to the mark later on. So here's my solution here. So I'm going to just swirl it around a little bit here. You can also use a stir stick to do this as well. Okay. So mash up some of this powder. You'll notice the approximate volume on the beaker is nowhere near 100. That gives me a little bit of wiggle room to actually, in case there's any leftover powder or I need to dissolve some more, I can dissolve that afterwards. So I'm just going to pour this into my volumetric flask here. So that's fairly good. I don't see traces of solid left over, but there may still be a little bit of reddish of the solution of cobalt nitrate. So I'm just going to add a little bit of water. Okay. Just try to rinse down the sides, rinse down the glass stir rod as well. And again, I'm just going to add these rinsings here. We want to make sure all the powder, as we have used, all gets in the volumetric. This beaker here now looks very clear, so that's good. And now what we're going to do is we're just going to add water directly to the volumetric flask. Again, near the bottom here, you have a lot of wiggle room. By the time we get up to the narrow neck here, you have 1 mark, really well calibrated for 100.00. I want to make sure when we get up to that neck portion here, you might want to actually use an eyedropper at eye level, bottom of the meniscus, to get to that mark there. So I'm just going to add a little bit of water. We don't really need to do this on the scale, but I'm just going to add it on there. So again, I'm pretty close to that neck part there. What we're going to do is we're just going to take a dropper, okay? I'm just going to soak up a little bit of solution here, and at eye level here, I'm just going to keep adding this water until it hits the mark. We don't want to accidentally go over, or else we need to start over again. So looking at eye level, bottom meniscus here, exactly at that mark there. So we have 100 milliliters. The volumetric here is the most precise. We can use a rubber stopper here, make sure it forms a nice seal on the top here. I can rock this back and forth, okay? Doesn't need to be too vigorous, okay? Just to make sure all the solution here has been fully dissolved into the mix here, okay? So we've created our stock cobalt-2 nitrate solution here. This actually came in the hexahydrate form, so you want to make sure you factor that in when you do molar mass. And when we come back, we'll talk about doing the dilutions. Thanks, guys. Okay, so I've taken our stock solution here and poured it back into a beaker, okay? It's always a good idea not to pipette, either it's a dropper or a glass pipette, not to pipette directly from the volumetric. It's nice if it's in a sort of wider mouth beaker here. The next part of this experiment here involves doing a few dilutions. So we're going to take our stock solution, we're going to follow the manual in terms of what to dilute here. We're going to line up our test tubes here. I have A, B, C, D, E. We're going to create an unknown on the far side here. Just to save a little bit of time, I've already measured the difference in volume of water that I would need. I put those in as well. So all I need to add to it here is my stock solution. So we're going to start off solution number A is not diluted at all. They want us to aim for about 16 milliliters at a time. I'm going to start off with the big graduated cylinder here. Looking at eye level here, we want to line it up to that 16. So I'm just going to add our cobalt 2 nitrate solution. For the rest of the solutions here, we are going to just follow the dilutions that we need. So second one here, we need 12 milliliters. So I'm just going to pour in another 12. It is the same solution, so you don't need to do any rinsings in between. So let's just go 12 milliliters. I'm going to add that to the 4 milliliters of water that were already present. Okay. Third one here, we need 8 milliliters. So I'm just going to pour 8 milliliters here. And then again, just add it to the test tube. This is test tube C. Okay. Sometimes test tube, they range in width, so it's not always obvious how much is in there. So test tube D here, I need 4 milliliters. So it might be hard to actually start measuring such small volumes in a big grad cylinder here. What we're going to do is we're actually going to use a smaller graduated cylinder. So I'm just going to add this to 4 milliliters. Again, looking at eye level here, I'm going to add that to the water. Test tube E is the last one here, so I just need 2 milliliters. So we're just going to try to pour out 2 in our grad cylinder. If you go a little bit over here, you just grab a dropper and I can soak up some of the extra that you don't want. So bottom of the meniscus here, you want it to be 2. I'm going to add that to our solution here. Now normally for an unknown here, this may have been after you've done a reaction of some sort here. I've just put in a random amount of water here. I'm just going to add up the difference here. And then using our spectrometer, we're actually going to figure out what the concentration of this is. Okay. So just making a very qualitative observation here, you'll notice as we've steadily diluted it in more and more water, we see that the color intensity actually does drop. So in the third part of this experiment here, I'm going to transfer these here to a pipette, and then we're going to punch it into our spectrometer and see how we produce our calibration plot. Thanks, guys. Okay, so we're just going to finish off our lab here. We have test tubes A through E. I've made an unknown solution by taking our most concentrated sample and diluting it with a little bit of water. We put them into their own individual cuvettes here, so that way we can put them into the spectrometer one by one. Remember, for your cuvettes here, usually 2 sides are clear, 2 sides are frosted. Because for our spectrometer, the light is coming in side to side, you're going to want to make sure that the clear side is also parallel to that light. If your cuvette is clear on all 4 sides here, we're fine. So I just started up a new window here in our spectrometer. We're going to start off by pressing the record button. It's going to first ask us to calibrate our spectrometer here. For a dark solution, it should know not to turn on the light here. If you're not sure, you can just cover over the sample chamber here. That way it can just sort of subtract off any background light for us. Next thing we calibrate for is our reference. So what I'm going to do is I'm going to put in our blank solution. Because the solvent for our sample here was water, I just fill the cuvette here with water. Again, double check that the clear side is side to side here. That way, this is our calibrating for a reference. It's going to subtract off as the light is trying to go through the plastic of the cuvette, as well as about 1 centimeter deep of water. It's going to automatically subtract this reference here from our solutions. So that should be convenient. All right, so it looks like everything is good. We're going to start off with our most concentrated sample here. This one here was supposed to be a rough 0.160 molar, so you stick that in first. First chart we get here is an absorbance versus wavelength graph here. We want to figure out what lambda max is, which wavelength of sending in is giving us our strongest signal, so that later on when I check the other dilutions here, we'll try to maximize the numbers and therefore minimize errors. Remember, our chemicals look red to us not because it's absorbing red. We see on the spectrometer here, it's actually absorbing the complement of red, which is somewhere in the green region here. You should be able to just scale the axes here by just scrolling there. It's sampling in real time, that's why it still might fluctuate from time to time. That's okay. I'm going to move my cursor here so I can sample lambda max. Again, so we're sending in about 518 nanometers, so sort of midway into the green region here. I'm just going to press a check mark just to confirm, yep, this is the lambda that I want you to be using for the leftover calculations. I'm going to just stop that. Then what we're going to do is we're going to toggle over to the concentration window here. When you first click over, there's some default concentrations here. These may or may not match the ones that you actually have made here. So if you want to use this sort of default built-in graphing software, you're going to want to make sure you edit these numbers. So let's do that. We'll press record, just confirming we are sending in 518. This one here is still sampling in real time, so that's why it's still fluctuating. I'm just going to type in my concentrations here. So I'm just going to double tap that there. Our most concentrated sample was roughly 0.16 molar. Second one down, I'm going to put in here a 0.12. Third one down, I have 0.08. These ones don't necessarily have to be in order, but because I put these ones here from highest concentration to lowest concentration here, I'm going to just do these in order just for simplicity. So 0.04 for that one, and we made one more, which is 0.02. Okay, and then all we have to do here is we're just going to individually put these cuvettes here into the spectrometer. We're going to tell it, yep, this is this concentration, and it's going to sample the absorbance for us. So I still have solution A inside from the previous absorbance wavelength graph here. Just going to toggle back there. Again, it's going to jump around a little bit here, especially if you're just taking the data and plotting it on Excel or Logger Pro later on. I would just get some middle value, give me a plus or minus to sort of capture some of the extremes. You can just press the check mark here. I'm going to just individually here put in the other solutions. So solution B, a little bit lower absorbance, perfect. So just check mark. This is creating what's referred to as a calibration plot. We're getting a relationship between absorbance as well as concentration. And that way, if I scan in my unknown solution, if I know the absorbance reading, Beer's law would actually give us the relationship with what the unknown concentration would be. So that's solution D. There's our absorbance reading, and then solution E. Okay. That one there was fairly faint here, so probably it's not even getting a signal here, so let's just keep it at absorbance of 0, fine. Okay. Now that's not looking like too much because our scale here is very off. Again, you can change the scale here by toggling these side to side here, because we're talking concentrations like 0.16 or so as a max. You can scroll it in here. What's nice here is you can actually just press this and it'll just maximize the sample window for us. Should we just pull this away here? Remember, the Beer-Lambert law says at very low concentrations here, there should be a linear relationship between how much of this wavelength is being absorbed versus concentration. Some nice features here that you can do inside this app here. Because it is a linear relationship, I can get it to fit to a mx plus b sort of relationship. It's telling us what our slope is along with the error, telling us what our y-intercept is, maybe some sense of systematic error, and this R sort of correlation coefficient telling us how closely our data is to this linear relationship here. So just one last thing for us to do. We've created our calibration plot. That could be done sort of built in as I just showed you here, or you can just take down these absorbance readings and put it into another software. I'm going to test my unknown solution. Okay. So my unknown solution here, it's 0. That one still will flicker here. I'm just going to press check mark there, so 0.25. Given this linear relationship here, we're expecting it's going to be somewhere between maybe the 0.04 and the 0.08. Because we do have the best fit equation here, you can just type in, what of my unknown solution, the absorbance reading I got was a 0.278, and we can get this formula here to calculate what the unknown concentration would be. Okay. The Beer-Lambert law starts failing when the concentrations get too high. So if the color intensity gets too intense, sometimes the light has trouble actually getting through. So it might start scattering. We sort of deviate away from this linear behavior. At that point, you just dilute the solutions down so that you can be back into this region here. If you do need to record transmittance later on here, remember you could just toggle back and forth here, absorbance and transmittance. If you like, you can plot what do the transmittance look like for these solutions here, but definitely it's not going to be as nice as the linear relationship we get for absorbance versus concentration. All right, thanks guys.